In this video, I'm going to show you a method on how to solve for the electronic geometry, molecular geometry, and hybridization of each elements in the polyatomic anion sulfite. The chemical formula for sulfite is shown here. It says here that there's one sulfur and 3 oxygen atoms. The first method is to write down the Lewis dot structure for each elements. So for sulfur, it has 6 valence electrons. Oxygen also has 6 valence electrons. Okay, so we do the same for all the 3 oxygens. Okay, the reason why I wrote this is to emphasize the chemical formula, SO3. Here, SO3 2 minus. 2 minus indicates that it has 2 extra electrons, contributing to the negative charge of this polyatomic anion. Now, this extra electron will be attached to a particular atom here in this in sulfite. So to determine which element the extra electrons will be attached to, we need another information, and we can see that information on the periodic table, and it is called electronegativity. And electronegativity is the tendency of the element to attract electron to itself. So for sulfur, the electronegativity value is 2.5. For oxygen, it's 3.5. The higher the electronegativity, the more capable the element to attract electron to itself. So what we're going to do here is, let's try placing this electron to this oxygen, and then this one here. As you can see, the electron is attracted to the more electronegative element, oxygen, rather than sulfur. Now, electronegativity can also help us guess which of these 3 is more capable of being a central atom. Here, oxygen, higher electronegativity, tends to attract electron to itself. Sulfur, lower electronegativity, tends to share more of its electron to the other surrounding elements with a higher electronegativity. So here we will place sulfur as our central atom. Having lower electronegativity, it tends to share its electron to the other elements with a higher electronegativity. Okay, so you can see 7, what we did earlier, and then here 7. Probably gonna place the other oxygen here on top. Okay, this one is 7, this one 7, this one 6. And after making a guess on which one will be our central atom, it's now time to form bonds. And we indicate bonds by using a line like this. Okay, here we're following the so-called octet rule for certain elements, and certain elements, particularly oxygen, follows the octet rule. That is, in forming covalent bond, it will share some electrons in order to have a total of 8 shared with it. Okay. Also, this one will only ask sulfur to share one of its electrons, so that now it will have 8. And then this one has 6, so it needs 2. Therefore, it will have to borrow 2 of sulfur's electron needing to do a double bond in order to do that. So this oxygen, as a result, will form a double bond with sulfur. And if you see, okay, I will just redraw the structure. Okay, it looks cleaner here. It's just the same, I just rearrange it. Okay, again, the extra electrons are placed here, and then emphasizing the double bond. If you count the number of electrons associated with sulfur, we will see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons for sulfur, and this is called an expansion of valence for sulfur. For oxygen, okay, now the reason for the expansion is that if we look at the periodic table, so you can see what's written here is sulfur and oxygen's electron configuration, and also their location on the periodic table. Okay, so you probably solve several problems at this point regarding molecular geometry or electronic geometry. Probably you will encounter carbon, nitrogen being a central element, and they strictly follow the octet rule. Meanwhile, if you encounter something like phosphorus, sulfur, chlorine, something here, and then even iodine, having more than 8, having an expansion, it is because here the valence electrons has access to the second energy level, and the second energy level only has access to the s and p orbitals. And how many electrons can the s and p orbitals can hold here in the second energy level? A total of 8. Okay, that's all they can hold over here. That's why these elements, carbon, nitrogen, when they become central atom, and then here oxygen, in our example, it will strictly follow the octet rule to have the same configuration as the noble gas neon. Okay, it's because of this, its electron configuration. Let's look at phosphorus, sulfur, and chlorine. The valence electrons of these elements has access to the third energy level. In the third energy level, the third energy level has access to S, P, and then D. Particularly for sulfur, this is the orbital notation. 3s2, 3p4. If it is necessary to form multiple bonds to have an expansion, it can have an access to the vacant d orbitals. Okay, that's why expansion occurs starting with central atoms that are located in the third energy level. That's why phosphorus can have an expansion, sulfur can have an expansion, chlorine have an expansion, because they can use the vacant d orbitals. Okay, so I will clear the screen and let's answer what is the electronic geometry and molecular geometry. This is very easy. The best way to know the electronic geometry and molecular geometry is to learn how to count electron groups. Okay, you need to count electron groups to determine the electronic geometry, molecular geometry of a molecule or a polyatomic ion. So in counting electron groups, you just make a table. Okay. Count the number of single bonds. Count the number of double bonds. Count the number of lone pairs. And then add the total. So for this structure, single bond, 2. Double bonds here, double bond. Lone pairs, 1. How many electron groups? 4. Okay, these electron groups, okay, as you can see, electron group 1, electron group 2, electron group 3, electron group 4, they contain electrons, negative charge. They have to be separated in space because, electrons repel each other. So basically, they will assume a particular geometry in space. Okay, that particular geometry, arrangement in space, as a result of the repulsion of the single bond to the double bond, lone pair to the single bond, that is called the electronic geometry. And we have a table for that. Here, for a molecule or a polyatomic ion with a 4 electron group, those electron groups will assume a tetrahedral distribution in space. Tetrahedral because, as you can see here, tetra, 4 hedral faces. Okay, let's say this one is the double bond, this one single bond, this one single bond, this one lone pair. Here, that is one face. This one makes another face facing us, and then this one is behind us. So you can see there's a face facing behind, and then there's a face facing downwards. How many faces can you see? How many surfaces can you see in this particular solid? 4 faces, tetrahedral. This, you can ignore this. Ideally, for example, this particular angle is the angle between 2 electron groups. This could be true if we're dealing with CH4, something like that. The same elements at the corners. But here, we're dealing with one double bond, single bond. Okay. For our structure for sulfite, it cannot achieve the ideal number of angle of separation because one electron group will repel the other more. Okay, this one, let's say double bond here, will repel more the single bonds here. This could be wider, so you can see this could be wider, making it greater than 109.5. So there are certain rules for there are certain observations for those. Okay, but at least we know that the electronic geometry for sulfite is tetrahedral. Now we move on to the molecular geometry. And what will help us determine the molecular geometry? Molecular geometry, we only focus on the actual, A here stands for atoms. The actual separation of atoms in space. This one is the central atom. So this is just, okay, letter C, central atom. For our structure, we have one lone pair. We have one lone pair. So this one is sulfur. It's a double bond with oxygen, single bond with oxygen, another single bond with oxygen. We're only concerned, for molecular geometry, we're only concerned about the actual geometry formed by the atoms, ignoring the lone pairs. So here, trigonal pyramidal. Okay. So you can see that's what a trigonal pyramidal looks like. So our answer for molecular geometry is, our answer here is electronic geometry tetrahedral, molecular geometry trigonal pyramidal. Now we can move on to the hybridization. So you can see the answer here is already given. Hybridization of the central atom for all species that are tetrahedral is sp3. You were often asked to memorize this, but what is the reason for that? Why is it always sp3? Okay, let's move on to hybridization now. To deal with hybridization, we need to write the orbital notation for each. Okay, for sulfur, we know that this is the electronic configuration, but we need the orbital notation. So for sulfur, 2, 3, 4. There you go. Okay. Now, to avoid confusion, I will be assigning this oxygen as, let us assign this oxygen as oxygen number 1. This one is oxygen number 2. And then this one is oxygen number 3. Okay. Here we have to take note that we added an extra electron earlier. So normally oxygen is 1s2, 2s2, 2p4, but I'm not going to write it here to avoid confusion. I'm not going to write 2p4, but take note that we have an extra electron here. Okay, basically hybridization, first of all, you can consult a textbook for the official definition, but here I'm just going to show you a method. For sulfur, this is the orbital notation for the sulfur atom. Now that, okay, 3s2, 3p4, I hope that's clear here. Now, if sulfur is going to form a covalent bond to form a molecule or polyatomic ion, there has to be a rearrangement here in order to cater for bonding to occur. And that arrangement that I'm talking about is that sulfur has to prepare not only sulfur but all these elements. They have to prepare half-filled orbitals. Okay? Sulfur will have to prepare half-filled orbitals in order to bond with oxygens. How many half-filled orbitals that does sulfur has to prepare? The number of half-filled orbitals that it has to prepare will be the same as the number of elements it will bond to. Okay, so this one, number of half-filled orbitals is the same as number of atoms it will bond to. What does that mean? Sulfur here only has 2 half-filled orbitals. It needs 3 half-filled orbitals because here it will bond to 3 oxygens. And sulfur, having access to its valence electrons having access to the third energy level, can basically use this, devacant the orbitals. Okay, in order to prepare 3 half-filled orbitals, this extra electron will move here. So you can see your sulfur created half-filled orbitals. Actually 4. I will explain what this for later, but at least it has 3 that is ready to bond with the other oxygens. Now, with regards to sulfur bonding with oxygen number 1, let's say these 2 orbitals will overlap, and the bond that will be formed is along the axis between these 2 elements. Okay, so, and this is called this is a single bond. It occurs along the axis of these 2 elements, and sulfur and oxygen number 2, let's say it's an overlap between these 2 orbitals. Okay, that's a single bond. Again, the bonding occurs along the axis. Now, for sulfur and oxygen number 3. Okay, first of a sulfur bonding with oxygen number 3, there's a double bond here. I will first address the first bond. The first bond is just like the other bonds that I talked about earlier. It's a, okay, I'm not gonna say single bond. It's along the axis. And this single bonds here that occurs along the axis, there's actually a special name to that. It's called sigma bond. Okay, so actually here, let's also say this is sigma. This is the symbol for sigma bond. I hope you can still see this. The earlier one is also sigma bond, the bonding with sulfur and oxygen number 2, sigma bond. Okay, this one is a sigma bond. The symbol is this, sigma bond. Now, for the second here, this one, for the second one, since, okay, let's perhaps we draw here, oxygen and sulfur. Okay. So, since the region along the axis of these two atoms is already occupied, the second bond here, let's say, okay, this half-filled orbital here. This one is half-filled. Okay. And then for sulfur, I forgot the image for a d orbital, but there's kind of donut thing here, as far as I remember. Kind of looks like that. Say this half-filled orbital here looks like this, half-filled. The second bond is just an overlap of these two half-filled orbitals. Okay, and this overlap of half-filled orbitals, sideways overlap. This particular sideways overlap, there's a special name to this. If this one is called a sigma bond, this one is called a pi bond. It occurs along the side. Okay, this one is a head-on overlap, as they say it on textbooks. Meanwhile, this one is a sideways overlap. Okay, whenever you deal with double bonds, remember the first bond is a sigma bond, the second bond is a pi bond. If you're dealing with a triple bond, then that is one sigma and two pi bonds, and I'm not gonna draw it here. Okay, now that's what happens. Okay, now let's look at sulfur again. So this orbital holds the lone pair, this one, yep, and then this one bonding with oxygen number 1, oxygen number 2, oxygen number 3. Hybridization. As you remember, the hybridization here is sp3. What is the reason for that? For this notation, sp3, we only count the orbitals that holds the lone pairs. Okay, and then also that participates in forming a sigma bond. Okay, so for this notation, for the sp, sp2, sp3 notation, we only count the number of orbitals that participate in holding a lone pairs and in participating in forming a sigma bond. So here we have 1, okay, 1s, this one is a p, this one p, this one p, and then simplified to sp3. Take note that here I just made it simple that you count the number of orbitals holding the lone pair and then participating in sigma bonding. But in textbook definitions, they say that the hybridized orbitals are equivalent orbitals. Okay, probably in terms of energy, something like that. But I'm just showing you the method here. We're not counting this extra orbital here, so it's not sp3d, it's just sp3. We're not counting the orbital that participates in pi bonding. Okay, so there you go. Show you the method, and I will be showing more problems like this in my channel, on my channel. Okay, so I hope you learned the method that I applied here in solving for the following, for several polyatomic anions. So with that, I hope you learned something, and thank you for watching.